So this lesson is about Cramer's rule. Cramer's rule is an alternate procedure to use matrices and determinants of matrices specifically to solve a system of equations. So here is our system of equations. X and y are the variables, and then a, b, c, d, e, and f are going to be various coefficients. I'm not going to derive Cramer's rule for you. I'm just going to give you Cramer's rule, and then you will have some practice problems to do, as well as your challenge will be to derive Cramer's rule starting with this system of equations and getting to the result which I have at the bottom. So let me first of all explain how Cramer's rule works. For Cramer's rule, what you do is you make three different matrices. The first matrix is going to be called the coefficient matrix, or C, and basically it's just the matrix made up of the coefficients. Now you've seen that before when we had to deal with, when we were trying to use inverses to solve matrices. So the A, B, D, E coefficients become the coefficient matrix. Now you have two other matrices. I'm going to call them n subscript x for numerator for x. And the numerator for x matrix, or the n subscript x matrix, is exactly the same as the coefficient matrix, but in the column where the x's were, where the x coefficients were, this column, you're going to throw that column away and instead import the constants from the answers. So these two values sit in here. Everything else is the same. So the y coefficients are exactly in the same place as they were before, and the x coefficients go away and instead the constants get put in. So that's the nx matrix. And for the ny matrix, it's exactly the same idea. You take the coefficient matrix, but this time, because it's ny, you throw away the y coefficients, and instead you put the answers, the constants, and then you leave the x coefficients where they are. So you get three matrices. One is the coefficient matrix. The second one is the nx matrix, which has new values in the x column, and then you have the ny matrix that has new values in the y column. And then the solution to this system, the x value is going to be the determinant of the nx matrix divided by the determinant of the coefficient matrix. And then the y value of the solution will be the determinant of the ny matrix divided by the determinant of the coefficient matrix. So it uses these three matrices, and you calculate the various determinants, and you do this particular fraction, and that gives you the value of x and the value of y that solves this system. So now I'm going to do it again, but this time I'm going to show you how it works for a 3 by 3. So here's a 3 by 3. You have ax plus by plus cz equals d, etc., etc. Remember, x, y, and z are the variables, and the a, b, c, d, e, f, g, h, i, j, k, l are all the coefficients and constants in the problem. So again, you're trying to solve for x, for y, and for z. We now need four matrices. You still have your coefficient matrix, which is basically the coefficients a, b, c, e, f, g, i, j, k. It's right there. You get your 3 by 3 coefficient matrix. And then the nx matrix takes the coefficient matrix, throws out the column that had the x coefficients in it, and instead puts the answers from the right-hand side in there. So there's that column. Everything else stays the same. So the y column and the z column are the same. Similarly, the numerator of y matrix is going to throw the y column out, put the g, d, h, and l in there, and leave the x's and the z's in where they were. And the z matrix and z matrix will throw the z column out and leave the x's and the y's in their place. So these four matrices, the coefficient matrix, the nx matrix, ny matrix, and z matrix, are made that way. And just like in the 2 by 2, the value of x will be the determinant of the nx matrix divided by the determinant of the coefficient matrix. Y will be det ny divided by det c, and then z will be det nz divided by det c. So you can see how this can expand to 4 by 4, 5 by 5, 6 by 6. All you got to do is create these matrices and calculate their determinants. And since you know how to calculate determinants of any n by n matrix, even though it might be a little bit hard work, it's much less work than trying to solve a system that has increasingly more variables. There's one more thing I want to mention, and it is, so sometimes you end up with no solution or infinite solutions, if you remember when you're trying to solve a system. And it turns out that the the determinants of these matrices also tells you which of those two situations it is. If the determinant of the coefficient matrix is 0, that means the denominator now is 0. You can't divide by 0. And all of the other determinants are also 0. So every fraction that you're trying to solve is 0 over 0, then you have infinite solutions. If the determinant of the coefficient is 0 and any of the others is not 0, so if nx is not 0 or ny, if any of those determinants are not 0, then you have a no solution situation.